All right, so we've got the last part of our problem to consider is t onto. So what that's really asking is it true that every vector in the codomain of t happens to appear as an output value? So in other words, is every vector in the codomain, does it appear as an output vector when you plug in some particular value in the domain? So, well, I don't know. Is it? How do you answer a question like that? Well, start by looking at a picture here as best you can, or draw a picture and say, okay, is there anything that you couldn't get? Maybe let's draw a fresh picture down here. Let's I'll draw a picture of the, just going to straighten out or what? Yeah, okay. So I'll just draw a picture of the x1, x2 axes. So we've got the origin right here in the middle. And let's just say, okay, if I had a point over here and I wanted to reflect it about the origin, well, that would take me down here, right? Okay. If I took a point over here and I reflected it about the origin, well, that would take me down here or something like that. If I had a point over here and I reflected it about the origin, it would go here. Okay, well, is there any point that you can't, that isn't the reflection of some other point? And well, not, the answer is no, right? Because if I start, think of it this way, if I start at any point and reflect it across the origin, it'll take me down here. What if I reflect it again? It's going to take me right back to where I started. So every point is actually the reflection of some other point. In fact, it's the reflection of its own reflection, right? So for that reason, that's the idea. If you start at a point and you reflect it and you reflect it again, you'll get right back where you started. And because of that, that's enough to prove that the function t is onto. So let's let's fill in, let's fill that in so you can, if you want to, let's make some notes about what we just said. So let's draw a picture here. So that's x. Let's draw a picture of t of x down here. So this is t of x. And then actually, x itself is t of x. Okay, and just one more time to go through it just to make sure we got the idea. Let me draw a brown dot, and then I can bounce this around on the picture. So if we have our vector x and we apply t to it, that's going to reflect it across the origin and send it down here. But now if we apply t again to this vector, we'll have t of x. Well, if you reflect t of x, it's going to send you right back up to x again. So that's why I can say that x is equal to t of x. So let's use that idea to prove that t is onto. So we'll do it here. So we're going to pick an arbitrary y. Let's write it in terms of its coordinates, y1, y2. That's an arbitrary vector in R2. And we're going to show that that's equal to t of something. There's some vector x that you can choose that if you apply t to the vector x, you'll get back to the vector y. So why don't we, well, since we just kind of made the observation that every vector is the reflection of its own reflection, and we want to show that this vector is a reflection of something, the thing we should take for the something would be the reflection of this vector. So let's take y, or take x to be t of y, which is, take the standard matrix of t and multiply it onto the vector y, which is y1, y2. And what you'll get here is, what will you get? You'll have, so I went too far here, we'll have y1 times negative 1, 0, plus y2 times 0, negative 1. And if you work this out, you're going to end up with negative y1, negative y2. Okay, well so in other words, that's what your x is going to be. Now let's say, okay, let's take t of x. I better be careful with how I use this spacer. I'll run out of room here. T of x would be t of negative y1, negative y2. And you'll see this gives you, if you apply the standard matrix, this is going to be negative 1, 0, 0, negative 1, multiplied by negative y1, negative y2. And that'll be what? How will that work? we're going to have, I think I can fit one more line here, we'll have negative y1 times the vector negative 1, 0, plus negative y2 times the vector 0, negative 1. And I'll carry on down here because I'm running out of space. This will give us negative y1 multiplied by negative 1. That's going to give us y1, 0. And then over here, multiply negative y2 in for 0. That'll give you 0. Negative y2 in for negative 1. You're going to get positive y2. So you'll have 0, y2. Finally, you get y1, y2, which is, hey, that's y. Right? So back through the main idea. We started with the assumption that we had a particular vector y in our codomain, which is R2, and we were able to construct, I'll just circle this part because this is really the main idea. We were able to construct a vector x that when you plug it into t, you end up getting y as a result. That's what these calculations show, right? So in other words, every vector in R2 shows up as an output vector from the function t. So t is onto for that reason. So we can say therefore t is onto.